last time we learned about the concept of wave, right? So wave is defined as a disturbance of a continuous medium that propagates with a fixed shape at constant velocity. So that's kind of a basic definition of a wave. And then we introduced the wave equation. So with the wave equation, looks like it's composed of second order derivative or along space coordinate, and then second order time derivative, right? So this is the bottom one. This is the wave equation for vector fields. And then we learned about like a few important definitions, like what is amplitude of wave, wavelength, wave number, period, angular frequency, or I usually just call it frequency, okay? So these are, you should be very familiar with these concepts like wavelength, wave number, period, and frequency. These are important things. And another thing is group velocity and phase velocity, right? The group velocity and phase velocity, what we learned was I just made an example of two waves superposed. And then if you have two waves with very similar omega and k, and these waves forms group, right? So like in this example, in the GIF image animations, the group velocity, the speed that group moves as a function of time can be very different from the phase velocity, right? The speed of a given phase point. So these two can be very, very different, okay? But again, like in our lecture, when we learn about electromagnetic plane waves, phase velocity and group velocities are basically the same. So you don't need to worry too much about this distinction. So what we want to do today is we want to derive the equations for electromagnetic waves from Maxwell's equations. Okay, so we know Maxwell's equation. Like, so we begin with free space and then move on to the materials without loss, like dielectrics, and then materials with loss. Okay, so we will see how it's gonna expand. So first, free space. So what I mean by free space is epsilon r and mu r is 1, right? Because there's nothing, no material. So relative permittivity and relative permeability must be 1. And then there's no source. So there's no free charge, no free current. So JF is 0, rho FV is 0. So this is very convenient conditions, right? So once you set these conditions, then Maxwell's equations can be reduced to these four equations, right? Divergence of E is 0, divergence B is 0, curl of E is negative dB dt, curl of B is mu 0, epsilon 0, dE dt. And then we begin with Faraday's law, curl of E, okay? Curl of E is negative dB dt. Then take curl on both sides of the Faraday's equation. From the left side, we get curl of E, okay? Curl of E means it is same as this, like negative Laplacian of E and then divergence of E of gradient of divergence of E. But we already know that from Gauss law, because we have source free, there's no source, divergence of E is 0, right? So we know that curl of E is just Laplacian, negative Laplacian of E. So this is very convenient. And the second thing is that the right-hand side. Right-hand side is curl, a negative curl of dB dt. And then curl of B is here in Ampere's law, right? So if you apply the Ampere's law, then curl of B is just mu 0 epsilon 0 dE dt. And then there's another d dt here. So you ended up having negative epsilon 0 mu 0 d squared E dt squared. Okay, so in summary, what you get for E electric field equation is Laplacian of E is equal to epsilon 0 mu 0 dE squared, d squared E dt squared. So this is wave equation, right? Second order space derivative and second order time derivative. It's connected with epsilon 0 mu 0. So this is wave equation. And then we know that if this is a wave equation, then what's written here, epsilon 0 mu 0, is just 1 over v squared, the speed, 1 over speed squared. So, and from this, we can easily know that speed of light in free space is 1 over mu 0 epsilon 0, right? 1 over square root mu 0 epsilon 0. And then if you actually calculate, plug in the values for vacuum permittivity and vacuum permeability, you can get the speed of light is actually 3 times 10 to the 8 meters per second. Okay, so this is how a wave equation for free space can be derived from Maxwell's equations. Okay, and similarly, you can do the same thing for H field. So if you want to do the same thing for the H field, what you need to do is to take curl on Ampere's law and then apply the other equations. Then you can get exactly same equation. Okay, so Laplacian of H is equal to mu 0 epsilon 0 d square H dt squared. Okay. So what I want to say in this slide is that Maxwell's equations can be reduced to wave equation in this, source-free conditions. So do we have any question here? I think this is important. I mean, for most of you, this thing is pretty new, right? So I recommend you to pay more attention on this topic because this is very new. Okay, so assuming that there's no other question, I'll just proceed. And before we go further, I want to introduce a few more mathematical notations for you, okay, which makes our lives much more simpler. So here, because this is an elementary class, we want to just work on time harmonic field. So what I mean by time harmonic field is that the fields, the only time dependence on the field is just a sinusoidal, okay? So although electric field and magnetic field both can be dependent on space and time, but we just assume that the time dependence can be written like e to the j omega t. Okay, so e to the j omega t is just the oscillating function, right? It's a sinusoidal function. And then you multiply the space dependence and then take real value, and this becomes your full form of electric field. Why you do this? Well, then it becomes much more easier because you don't need to worry about time and only consider the space dependence. And of course, this is not valid for all cases. We just assume it that we are only considering a time harmonic field. And then the name for the full form, ERT, E of RT, is called instantaneous form. okay, instantaneous form. And the E of R, what's inside here, is called time-independent phasor form, okay? And of course, E of RT, the instantaneous form, is a real number because we just took real part of this thing. So ERT is just physically measured electric field, and it's called instantaneous form. But E of R, what's inside here, can be a complex number, right? And then if you and of course E to the j omega t is also complex. So complex multiplied by complex result in another complex, and then you take real part of it, and you get the real field, right? Why we do this? Well, you will realize that it's much more easier to deal with, you know, to deal with complex numbers rather than a real number. So, for instance, like if you want to say multiply two sine functions, then it's very difficult thing, right? Let's say you think about like sine omega 1t plus sine omega 2t. The summation and multiplication of the sine functions are very difficult. The real functions are difficult. But if you write things in complex form, then the multiplication is just an addition or subtraction in the exponent, which is very convenient. So the reason why we do this, because its exponentials are much easier to manipulate than sines and cosines. That's the reason. So there's a simple exercise, like find the instantaneous form of which phasor form given as E of R is AX E naught E to the minus JKZ. Okay, how we do this? We just multiply E to the J omega T to phasor form. So your full form like this, right? And then you take the real part of it. So epsilon 0, I assume epsilon 0 is real number, so you can just take it and go out. And then E to the minus JKZ multiplied by E to the J omega T is just E to the J omega T minus KT, right? So if you take the real part of it, it's just a cosine function of omega T minus KT. So let me know if there's anything unclear here. So in this slide, I just introduced you the notation. So two notations. One is instantaneous form, which is kind of full form of electromagnetic field. The other is phasor form, which is a complex number that is only dependent on spatial coordinate. And then the conversion between these two can be done by this equation. Because this is just definition, I guess it's not a big deal. Okay, Park Se-hoon asks at page 18, can we simply reduce del x dB dt, curl dB dt to, oh yes, okay. So what his question is that can we, so he's talking about a this part from this equation to that equation. We just switch the order of the differentiation, and yes, this can be done. So these two derivatives can be always switched. Why? First of all, it's a linear and commutative operators in this case, so you can just switch it. So yeah, don't need to worry about switching these two. Okay, so is there any other question? Okay, if not, I will just proceed. So now, using phasor form, our lives become much easier. So the beauty of the phasor form is this: like if you have a time derivative, then actually this can be written like this in phasor form, and then time derivative only applies to e to the j omega t, right? So this is actually j omega e to the j omega t, right? If you take derivative on the e to the j omega. So all time derivatives in time harmonic form can be just replaced by j omega, multiplication of j omega. So the equations on the left is the full Maxwell's equations. Okay, so D, rho, and B, E, everything just depends on both R and T, space and time. And then what's on the right are the Maxwell's equations in phasor form. And here we just assume time harmonic dependence. So all the time derivative becomes just the j omega, replaced to j omega, right? So the equations are much simpler here. And then we only need to deal with E field, B field, and all these fields only they are space dependent. Okay, so now let's play with this new sets of equations. New set of equations. So the free space electromagnetic wave equation now becomes, because it involves second order time derivative. Now you have, so second order time derivative is basically just j omega times j omega, right? Two time derivatives. And then jj becomes -1, and then omega squared. So this equation is very simple, like only time space dependent and very easy to solve. So here, and even this equation though, there can be many solutions. Like there can be spherical waves and then cylindrical waves, and there are many ways to solve these equations. But in our lecture, we only are interested in plane waves. So if you look at the title of the page, it's called monochromatic plane waves, right? Monochromatic, so mono is one. Chromatic is color, okay? So one color plane wave. And so monochromatic means, and color, of course, color of light is determined by its frequency. So monochromatic means we are gonna only deal with one omega, right? So that's what monochromatic means. And then plane wave means its constant phase surface forms infinite plane. So what does that mean? So what does that mean is that you can see the train of phase front, like if you look at this equation, I mean this GIF animation, you can see a wave is propagating along this direction, right? And then we set this direction to be z direction, okay? Then this wave is propagating along z direction, and then its constant phase surface is always parallel with xy plane, right? And so in that sense, this is called plane wave because its constant phase surface is forming plane, infinite plane. And similar manner, if somebody say spherical wave, that means your constant phase surface have spherical shape, right? So this is, but here we are gonna only focus on plane wave. Plane wave. Okay, so now because we know that we have this wave is propagating along z direction, right? And then along xy direction is nothing is changing. So the Laplacian can be reduced to z derivative, right? Because we know that dx and dy of electromagnetic field will give you 0 because nothing is changing in those directions. So for the plane waves propagating along z direction, this equation can be further reduced to this. Very convenient. And then we also define k here is epsilon 0, mu 0, omega squared, and square root of it. And this is called like a free space wave number. Okay, so why this is called free space wave number, you will get to know soon. So now you have this equation. This equation, everyone knows the solution, right? Just the second order space derivative, and then k squared. This is just the general solution for this is sine and cosine wave, right? Or you can also write it into e to the j minus jkg and e to the jkg. So this is the general solution, right? E to the minus jkg and e to the jkg and some coefficients, right? And these coefficients, of course, is undetermined. And then if there's a boundary condition, then you can determine condition, right? So here I also mark the first wave, e to the minus jkg, as the wave traveling in positive z direction, and then e to the jkg as a wave traveling in negative z direction. And this is because our time derivative is time dependence is e to the j omega t. So if we combine space dependence and the time dependence, for the first term you get omega t minus kg, and the second term you get omega t plus kg. So when time increases, the first term z should also increase, but the second term, when time t increases, z should decrease in order to keep the same phase. Okay, so this is the general solution for plane waves propagating along z direction in phasor form and instantaneous form. Okay, so is there any question so far? So what I wanted to convey here is that the first Maxwell's equation can be reduced to wave equations for E field and H field. And then this wave equation can be solved with some assumptions. And then here what we assumed is that the wave is monochromatic, meaning that its time dependence is just e to the j omega t. And then second, it's a plane wave, which means it only changes along the propagation direction, but the perpendicular directions, it doesn't change at all. And with these assumptions, the wave equation was simplified like this: d squared dg squared plus k squared. And this equation, we know the general solution, and we can solve it, right? So that's how our logic went. So do we? Okay. So just leave the question if you have any. I'll just keep going. So now oh, okay. Park Se-hoon asks again. Okay, so he's curious about like if we do not assume this is monochromatic, or if this is not a plane wave. Can we solve the equation in the same manner? Well, then this is not the only solution, right? I mean, of course, this is one of the possibilities. I mean, the reason we make assumption is to reduce the possibilities into very, very small degree of freedom, and then we want to solve it rigorously. But if we do not assume these things, then this, of course, is one possible solution, but it's not the solution. And but what I want to make sure is that, I mean, this is a really good point, because even if we do not assume monochromatic wave, any wave can be expressed as a linear combination of monochromatic waves with different frequencies, like we did, like we solved a electrostatic boundary condition problem using series solution. So what we did there is that we made a basis functions, right? And then you express like arbitrary function, arbitrary potential function as a series, linear combination of these basis functions, right? And we can do the similar thing here, even though the situation is not monochromatic, or even though it's not plane wave, we can write the situation, describe the situation as a series of plane waves with different k vectors and different omegas. Okay, so in that sense, this solution still is important. I hope this explains the question. Okay, so now let's think a little deeper about the monochromatic plane waves. So as I said, so let's choose just for positive propagating wave, okay? Because everything is basically the same, so I just choose one to make our problem simpler. So then the Phasor form is some coefficient times e to the minus jkz. And then in instantaneous form, it's e to the j omega t minus kg and take real part of it, right? So this is the positive propagating plane wave, monochromatic plane wave. And then we want to prove some important properties of the electromagnetic plane waves. So first, what we want to say is that E field and H fields are perpendicular to the direction of propagation. So what does that mean? So let's look at the individual Maxwell's equations again. So for the source-free Maxwell's equation, curl of E is 0, curl of H is 0. Both of these are 0, right? And then if you take curl of E here in this equation, then this is also convenient. Like you can just have a, I'm sorry, this is not curl, divergence of E and divergence of H is 0. And then if you take the divergence of E, then you realize that the divergence only because you only have a Z dependence, d dx or d dy is 0, and you have only Z component contribution, right? And then, because this must be 0, what does that mean is the Z component of the E field and the Z component of the H field must be 0, both of them, right? So by applying the individual Maxwell's equations, we know that the Z component of E and H field, both of them must be 0. What does that mean? Well, the wave is propagating along Z direction, right? And then there is no E field and H field components that is parallel to Z. So that E and H field must be perpendicular to the propagation. Okay, so that's one implementation, one important implementation, implication of this equation. And the second is that E and H field are perpendicular to each other. Okay, so because E and H field are just perpendicular to the direction of propagation, let's assume that E field is along X. Okay, because we can just choose it. Let's assume that E is just along X. Okay, then what we know is that the third equation, curl of E is dB dt, right? And then this equation, which is the Faraday's law, we know that H and E are perpendicular, right? And then you can actually obtain the relation, the actual quantitative relation between E and H by using this equation. So if you apply this equation, that you know that H field must be along Y direction if E field is X direction. And then the amplitude ratio is like this, E0 times K divided by omega mu naught. Okay, and if you insert K, the definition of K, then you know that this term is actually epsilon naught divided by mu naught and square root. Okay, so what I want to say is that, oh, by the way, the final note is that if you choose E and H field like this, then the final equation of Maxwell equation is also satisfied. Curl of E is the is also satisfied. So everything is happy. So again, summarizing, if you have an electromagnetic field propagating along Z direction, and then electric field and magnetic field must be perpendicular to the propagating direction, right? And then E field and H field are also perpendicular to each other. And then they are oscillating as a function of time and space. And also the amplitude of the E field and the amplitude of the H field are differ by this amount, epsilon 0, mu 0, square root of epsilon 0 divided by mu 0, and this is called impedance, wave impedance. Okay. And Dak Jun asks, was the fact that curl of E is negative j omega mu naught H derived from one of the Maxwell's equations? Oh yes, yes. So let me show you. This equation, right? So this is Faraday's law, and because time derivative is just j omega in time harmonic assumption, and then B is just mu H, so you can just reduce this equation into this, right? Right. And the fourth equation is also Ampere's law. So we are basically applying all four Maxwell's equations in this case. So we now know that our solution satisfies not only the wave equation, but also all individual Maxwell's equations, right? So this is a proper solution of Maxwell's equation. And this is also an important contribution by Maxwell. Maxwell figured out that actually light is a form of electromagnetic wave. Okay, and then electric field and magnetic field are just oscillating like this, which is a big discovery. Okay, so now let's go a little more general. I mean, there's no problem setting the propagation direction as Z direction, but just to be more general, I want to set the propagation direction as AK. Okay, so if we set the direction of propagation as AK, and then your K vector, the wave vector, means K is equal to K AK. K is just, here you know the notation. The bold face is vector, and the italicized normal face is just typeface is scalar. So if you do that, then the monochromatic plane wave solution in a phasor form is e to the j k dot r. Okay. In our previous example, k was just k a z because we only have z direction. But like if it's a random direction, general direction, then it should be k dot r. And similarly, instantaneous form should look like this. But and the same thing can be done here. Like if you look at this, divergence of E is 0 is actually equal to K dot E is equal. And then divergence of H is 0 is also equal to K dot H is 0, which means E and H are perpendicular to K in general, right? And then E and H are perpendicular to each other. Again, if you apply this equation, then curl of E is actually negative JK times E cross E. And then this is the right-hand side of the equation. So from this, you can get H as a K cross E divided by omega mu 0. And then you can just keep expanding these terms into like this, right? So epsilon 0 divided by mu 0, AK cross E. And then 1 over this value is defined as a free space impedance, as I said before. Okay, and free space impedance is about 377 ohms. I guess I was a little fast explaining this thing, but the message, I guess, is delivered, right? It's just we in previous examples, we just assume that the propagation direction of wave is z direction. And then here we just assume that it's going in a general direction, AK, right? And even we do that, we can still prove that E and H are perpendicular to the direction of propagation, and then E and H are perpendicular to each other. There's no problem doing that. And some of you might question that how come divergence of E is equal to K dot E? Well, it's actually not exactly same as K dot E, but it's same as minus JK dot E. But just try it because E field has a dependence of E to the minus JK dot R. So if you take divergence of it, then you will know that this minus JK just going down, and then dot E is basically equivalent. And similar thing applies here. Curl of E is minus JK cross E. Okay, that's the convenience of having exponential dependence. Anything, if you encounter any differentiation, you can just put this thing and then making it in front, and then just take the cross product or dot product. Okay, so any question so far? I hope it's not too complicated, right? So I guess the next step is to moving on to this situation with materials. Like so far we have no material. We assume this is a free space. but we want to move on to the case that we have material. So let's, oh, okay. Before then, I need to explain about the concept of polarization. So we learned about like polarization field in electrostatics, and that's different from this, okay? The polarization in the context of electromagnetic field is different thing. So here, as I said, electromagnetic waves propagating along z direction, electric field just need to be perpendicular to the k, right? And then E and H needs to be perpendicular with each other. That's the only condition. And because of that, electric field can have either X component or Y component or both. No problem doing that. And then we want to express the electromagnetic plane waves propagating along z direction as a linear combination of these two waves, X polarized wave and Y polarized wave. So what I mean by polarized here is that the direction of electric field oscillation. So if the electric field oscillation is along X, we call it as X polarized wave. And then the oscillation direction of the electric field is Y, it's called Y polarized wave. And of course, the general wave is the linear combination of two, right? Linear combination of two. And then if you look at the dependence, both of them has e to the minus j kg, and here also e to the minus j kg because it's propagating along z direction. But we have another factor here, plus j phi x. This is not dependent on the spatial coordinate, but just we call this as a phase vector, okay? E to the j phi x, and then e to the plus j phi y. And of course, this phase vector can be multiplied by E0, and then this entire thing can be a complex number. But here, we just write EX, E0x, and E0y as just a real number, and the e to the j phi x and e to the j phi y becomes just a complex term. Okay, just for convenience. And then, of course, the full form. So this is the Phasor form, and the full form, instantaneous form, looks like this: E0 cosine omega t minus kg plus phi x, and then E0y cosine omega t minus kg plus phi y. Right? Now, depending on the relation between phi x and phi z, the electric field direction has a very different behavior. So first one is the case of linear polarization, what we call as a linear polarization. So here, the difference between phi x and phi y is a integer multiple of pi. Okay, integer multiple of pi. Then, if this is like phi x, then this is like pi plus phi x. So even though we add pi here, it only flips the direction, but basically it's still cosine dependence, right? There's no problem, no problem. So in this case, E field oscillates like this as time goes by, the first figure. So it's just electric field vector increases and decreases along a linear path as time goes by. Okay, so this is, and the angle between x and y is determined by E0x and E0y ratio, right? So this is called linear polarization. And the second case, second special case, is that E0x and E0y are exactly same, okay? But delta phi, the difference between phi y and phi x, is a half integer multiple of pi. Then what that means is that if one of the equation is cosine function, the other equation becomes a sine function because they are differ by half integer pi. So that's if you like say cosine theta plus pi over 2 is actually a sine function. So these two has is one of them is written as cosine and the other should be written as a sine, which means the tip of a electric field vector should rotate as time goes by. And because Ex and E0x and E0y are the same, it forms a perfect circle. And this polarization is called circular polarization. And of course, depending on the direction of polarization, direction of the rotation, we can call this as a right circularly polarized or left circularly polarized. So here you can see the GIF animations. The direction of propagation is this along Z direction. And then if the rotation of the electric field satisfies right-hand rule, it's called right circularly polarized. And if it satisfies left-hand rule, it's called left circularly polarized. Okay. It's a bit complicated, but like polarization is one of the most important property of light, electromagnetic wave. And then if none of these are true, then we call this as an elliptical polarization. The polarization is, is drawing some ellipse or even more strange path on the plane. Okay, so Park Jun asks, why does phi x and phi y differ in the first place? I would ask, why not? Okay, if there's no restriction that they cannot be different, then we should, like in general case, they should be, right? That's what we consider here. So what we said earlier is that only talking about the Z dependent and T dependent, and the phi x and phi y are not, none of this. So it can be different. Yes. So as Bakjun said, it's just a general case. We are just dealing with the general case. And of course, what I mean by general is not like fully general. We are still in the regime where we are in a monochromatic plane wave. So we are still dealing with monochromatic plane wave. Okay. But the direction of the electric field can be changing as a function of time, because what we know from the previous discussion is that electric field and magnetic field needs to be perpendicular to each other. And then they are also perpendicular to the direction of propagation. So nothing prevents electric field and magnetic field rotate as time goes by, right? As long as they are mutually perpendicular and then perpendicular to K, they can do anything. So that's what we are dealing with here. And we want to classify the behavior of this polarization as linear, circular. Okay, so I imagine it's getting more and more difficult, right? It's like this is pretty new to most of you, but in terms of complexity, this is not that high. Like if you think about how difficult this is in terms of mathematical complexity, it's easy, right? It's just a new concept. And then what is needed is the ability to connect these equations to a physical kind of imagination, right? You need to connect the equations to the real world, and that's what is probably difficult. So I recommend you to ask many questions in this problem. Okay, so before we finish, I just want to go through just one more slide, this one. And now we move on to the regime where we have a material. And we first want to deal with lossless media, which means conductivity of a material is 0. Okay, why conductivity of material matters? Because if the conductivity is non-zero, that means if you have an electric field, you have a current, because conductivity relates electric field to current, right? And if you have a current, then current produces heat. So that's an energy loss. So when we say lossless material, that means sigma to be 0. There's no conductivity at all. Okay, and we also assume source free. There's no free charge, no free current. Then the equations becomes like this. Okay, so the only difference is that everything is basically the same, exactly the same. The only difference is the epsilon 0 becomes epsilon, mu 0 becomes mu, right? Because it's not a free space anymore. So epsilon and mu can be different from its vacuum value. Okay, and then if you plug that in and then rearrange the equation, you realize that the equation form is exactly same, but only the k vector changes. And the k vector was square root of epsilon mu omega, and previously this epsilon mu and epsilon 0 and mu 0. So compared to the vacuum case, so in order to say vacuum case, I put a 0, like a subscript 0 here. Compared to the vacuum case, you need to multiply n here, and n is defined as square root of mu r epsilon r, the relative permittivity and relative permeability. So this value is called refractive index, or index of refraction, or in Korean it's 굴절률. Okay, and because most of the material mu r is 1, non-magnetic. Okay, even almost all the material mu is 1, and then epsilon r is typically larger than 1. Okay, so n, refractive index, is typically larger than 1, right? It can be 2, 3, but usually it's in between like 1 to 3. Okay, so what does that mean? That means wave number increases compared to the free space case. And the increase in wave number means decrease in wave length, right? Because wave number is 2 pi over lambda. So in the material, wavelengths of light, wavelengths of electromagnetic wave get shortened, okay, at the same frequency. That's one important implication. And the plane wave solution is also the same, exactly same, because the wave equation itself is exactly same. All the solutions are just exactly same. The only difference is the value of k vector, right? And then also the impedance thing. Impedance also is defined as a square root of mu over epsilon. And now here mu is not mu naught, epsilon is not epsilon naught. So it can be different from vacuum value, but that's the only difference. The mathematical form is exactly the same. So now if you calculate the wavelength, as I said, it's 2 pi over k. And because k is increased, wave is decreased by factor n. N is again refractive index. And similarly, phase velocity, which is omega over k, can be also calculated. And the phase velocity of a light in a material is slower than phase velocity of light in free space. Again, by factor n. Okay, so I guess this is easy, right? It's all we did is just replace epsilon 0 and mu 0 to epsilon and mu. All the other things are exactly the same. And then next time, what we are going to learn is the case when we have a conducting material. So sigma becomes non-zero anymore. Okay, then what happens? As I said, when sigma is non-zero, then electric field can cause current, and current produces heat, and that's an energy loss. So in that case, as the electromagnetic wave propagates, its amplitude decreases because it loses its energy as a form of heat. And you can see that phenomena can be rigorously derived from Maxwell's equations. So that's what we're gonna learn in our next lecture.